Okay, thank you very much for coming. Welcome to this week's Museo Nacional de Ciencias Naturales research seminar. So I'm really pleased today that we have visiting us from Germany, Karina Winkler, who is a postdoctoral researcher at the Karlsruhe Institute of Technology. So Karina studied for her bachelor's degree in Gießen and did an MSc then at Tübingen, both in Germany. And then she conducted her PhD with supervision from Wageningen University in the Netherlands. Was your degree in geography? Yes. Yeah. So Karina is a geographer with a focus on geoinformatics and remote sensing. Her research focuses on modeling global land use change at high resolutions and the implications for climate change. So she studies areas including drought, deforestation, and the effects of land use on carbon sinks. And she's also interested in areas such as open data and knowledge transfer about land use change to the non-scientific public. So thank you very much, Karina, and we're really looking forward to hearing your presentation.
Thank you, Rob. Also, hello and welcome from my side. It's a pleasure to be here in a place so full of history, and also to talk a little bit about the topic that started in my PhD project, global land use change. We're looking a little bit into the more recent history now. Land use change can look like this. This is a very prominent picture of tropical deforestation for palm oil production in Indonesia. Land use change can also look like that. Urban expansion. This is a picture of Istanbul by night taken from the ISS. And land use change can also look like this. This is an example from Germany, from an open pit coal mine field. You can see it on the left in northwestern Germany. So when talking about land system change, we talk about land use and land cover change. Land use describes the purpose of how we use the land, while the land cover describes the biophysical properties of the land surface. Why do we care? So land use change is all around us. Over 80% of the global land surface has been managed during the last millennium. Land use change is also the second largest contributor to greenhouse gas emissions. The first one would be fossil fuel combustion. And land use change is entangled with many drivers, and land use change happens when we as a society place more and more demands on the land surface. And the land use change itself impacts the environment and also the society, and there's this continuous feedback. When talking about the planetary boundaries, this is a famous visual of the planetary boundaries, we see land system change as one major aspect, and the indicator would be the forest area that is still there as a percentage of the original forest area. And to stay below the boundary, to stay in safe condition for the planet, we would need around, like this threshold is set to be 75%. But currently, we only have 62% of the original forest still in place. So we are already in the zone of uncertainty where the risk is increasing of being even in the red area, in the zone of high risk. And when we look at the map globally, what's happening with these original forests, we can see that temperate forests are especially affected. So there's only 50% of the original temperate forest cover still in place. So we face these global challenges, and when we talk about land use change, we have to talk about agriculture. And agriculture is more than 1/3 of our global land surface. And we come from a long history, maybe not so long, maybe more recent, but which started or has much to do with the Green Revolution, where agriculture production has changed, efficiency has changed, and also the area has expanded more and more into former natural ecosystems. We face challenges when talking about agriculture, about food production. The main challenges are, of course, the global growth of the population, but not only this, it's also the consumption patterns that change within this demographic change and development. We produce more than enough food for feeding all people, but this food is not distributed well. There's a lot of power relations and unequal distribution involved in it. And of course, we have this huge environmental impact that is part of agriculture production, where agriculture expansion and also intensification affects the climate and the biodiversity. And the ecosystem degradation is also feeding back into the food production itself. So we have this, the picture depicts this a little bit as a triple threat to the Anthropocene, where we have climate change, biodiversity loss, and food insecurity, and somehow we have to handle. So this is a little bit the motivation for the project I started in my PhD about looking into past land use change and using as much data as possible to understand the transitions which we are facing. So for making some informed decisions about future land use and doing proper planning, we need to understand and we need to learn from the past. And the problem that lies with the land use data is that there's often two different kind of data. There's, at the one hand side, we have long-term land use reconstructions, which are used in the climate modeling community, in the ecosystem modeling community, but they lack detail, especially in terms of spatial resolution. They're often modeled themselves, have very coarse spatial resolution, and rely on only few observational data streams. And on the other hand, we have Earth observation. We live in an era of constant observation. We have so much satellite available surrounding us, and there's more and more open access data becoming available. But these high-resolution observational data sets are often not well connected to the long-term land use reconstructions. And this is why we come with an approach of linking those two worlds and creating a new land use data set that uses the information of both sides. So we're going to deal with three main research questions today. First one is, when and where did land use change happen on a global scale? So talking about the spatiotemporal dynamics. Then we're touching upon the underlying drivers of land use change. And of course, talking a bit about what are the impacts of land use change. Maybe not all questions are properly answered with the data set, but it's just a little bit showing on what is possible when you use different kind of data. Talking a little bit about the approach. So the data set is called HILDA Plus, Historic Land Dynamics Assessment. And as I already mentioned, we're bringing together two different worlds, the remote sensing and the land use statistics, mainly from the FIO database. And starting with the remote sensing side, we have so many data sets out there. There's so many data sets available that mainly contain land cover information. Here, prominent data sets, for example, are all the ESA data streams, ESA CCI land cover that covers land use from 92 to now, basically on a yearly basis, on a 300-meter resolution. But we have also higher resolution data like ESA world cover, 10-meter resolutions, global scale data set. And so with this example already, we see that there's different time spans, different spatial resolutions, also different land cover categories, which is a major problem when bringing data together. And that's why you need a lot of data pre-processing, lot of work on a computer to crunch these data and to get, to agree on a common land use categorization. So here is the, the 6 main land use categories used in the Hilda approach, and also bringing them on a common grid. So for Hilda, we used a 1 kilometer spatial resolution as kind of the common agreement of those different data sets. So we had to do the pre-processing. That worked like this. We have the original land cover map here visualized as a grid. And we have different land use categories at different grid cells. And we translate or transform the original data into land use masks. So for each category, we have a binary mask of where each land use occurs. And in the next step, we do resampling procedure that translate this original resolution data to our target projection, target grid. And then we have cursor cells, and in these cells are float values that give us the fractional coverage of each land use category. And we use this fractional coverage as a probability map or likelihood map, which show us how likely is a certain land use class occurring in that pixel. And this, we do that for all the years that are covered by the different data sets. And we bring all the different data sets together by averaging this likelihood. What we also take from land use, from the remote sensing side is we calculate for every country across the globe a transition matrix, which shows us which land use categories were converted into which land use category for every year. And this is very important because we don't only talk about net land use change, like cropland changed by 20% or so, but we talk about all the different, like how much cropland has been lost, how much cropland has been gained within a certain time span. Now we come to the second part of it, which is then all these land use inventories. And here we mainly use the Food and Agriculture Organization database, FAO-STAT, which gives us the net land use change for the different land use categories for all the countries across the world, but it's only at the country level. So for each country, we have one value of how much cropland or how much forests have changed in hectares and so on. We calculate this net change with our land use transition matrices from the remote sensing side to have a full land use transition matrix for all the countries. And this helps us, or this guides then the change allocation model. And we allocate land use changes then on those grid cells where it is most likely or most probable that a certain land use category occurs. So this is mainly the methods part of how such a harmonization is constructed. So Hilda Plus brings together remote sensing and the statistics, and the data harmonization project. Now there's 2 versions published, so this second version is just recently published. I didn't put the link in it, so that's the first paper, 21, and then on the same platform on Pangea, it's an open data set, everyone can use it, and yeah, so it's also a process of current development, so there will be another version at some point in time. Looking at the spatiotemporal patterns, our first question, what do we learn from this data, and how much land has changed, where and when these changes occur? This is a map of the land use changes. So we see here areas which has changed only once in the period from 1960 to 2019. This is single change events. You can see them in yellow, those areas. And the red color shows areas where there have been multiple changes in this period. And with change, we mean here a transition from one of these 6 land use categories to another, from one year to the other. And what we find is that it's 1/3 of the global land surface that has changed, which is more than other data sets have estimated, especially those long-term land use reconstructions that are used in climate and ecosystem modeling at the global scale. So we see that there's more growth changes that have occurred in that time, and these can be visualized with the dataset. When we look at forest change, we see that there's spatially divergent patterns. So here in green, you can see all the areas that has remained forest in that time, so stable forest areas. In blue, you can see areas where forests have been gained, and in red, you can see areas where forests have been lost. And the violet areas are, again, areas where there have been dynamic changes. So, for example, forests have been lost in 1960s and then later gained again. So there's some gains and losses in this period. And what we see is, of course, the prominent example of deforestation, forest losses in the tropical regions of the Global South. So you can see that here in the Amazon, in African tropics, and also in Southeast Asia. And in contrast, we see forest gains, but mostly happening in the global north. For example, here in this northern Siberian forest transition. And if we look at croplands, the picture is reversed. We see cropland gains, maybe not super visible here, but in the tropical regions of the Global South. And we see cropland abandonment, cropland loss in global north. And cropland abandonment is mostly the giving up of agricultural land use, and this often had to do also with political changes, regime shifts. So in Europe, we see some regions where these cropland abandonment areas are quite large. Also in southern Europe. There's many different reasons, but so here we can see this divergent pattern as well. We can also track the land use transitions and changes over time. This is an animation showing the land use in the Amazon region and how it changed from 1960 to 2020. If you look at the forest areas here in green and how they are more and more invaded by agricultural use. So we have the yellow part, which is pasture and rangeland use, mostly for cattle farming. And we have the cropland, which are in lighter orange color. So you can see how even at a 1 kilometer resolution, which is not super high resolution, but you can see how much impact this had on this formerly very compact forest area and not managed forests. We can track land use changes over time. So this is just some plots on the global and also for some world regions, the rate of land use change is the yearly rate. And we identify, when looking at the rate of land use change, this is here in area, we see different phases where the change has happened either quickly or a bit slowed down. So we see acceleration and deceleration phases. This can be, of course, analyzed for different regions across the world. And with the acceleration and then this sudden deceleration, this can have to do with the economic crisis and also with some influences of trade and globalization. So we have to further look into how much the speed of land use change is affected by different drivers. Land use transitions can be, again, classified. So we look at the same period, like from 1960 to 2020, and we classify each pixel of land use change into one of the land use transitions. Maybe we don't have to look at all the transitions here, but importantly, here the light red and the light orange colors are areas where agriculture has expanded into non-forest natural areas. So it's not deforestation areas, but where agriculture has expanded into savannas, into grassland systems. And we see pink and red areas where deforestation has happened, where agriculture expansion occurred into formerly forest ecosystems. And what is striking here is that the area where agriculture has expanded into non-forest ecosystems is more than twice as large as the expansion into forest. And yeah, this shows also the importance. So we talk a lot about deforestation, about tropical deforestation. It's an important topic. But sometimes savannas and other non-forest ecosystems of the global south or of the tropical, subtropical regions are a bit neglected. Although there's a lot more, space-wise, it has had higher impact in the recent past. Land use transitions over time, you can do this analysis for many different world regions. I don't want to go into detail here, but you see, sometimes you can see shifts across world regions and across time. For example, when we look at South America and Africa and we see this pink and red, and also the violet, the purple line, which are all areas where forests have been lost or degraded, then you see that there's a shift from the South American continent to more here Africa, where here agriculture expansion occurs more in the later part of this research period. So yeah, this often had to do with trade connections, with exports coming from the regions. Yeah. When talking about land use, this was mainly what I was showing was mainly about land use change being the transition from one class, one land use category to the other. But there's also this large component of the way we manage land, the land management, all the inputs we put into a system from the agricultural side. If it's water, fertilizer, pesticides, there's a lot of agriculture inputs used. We can also change the crop varieties, change the cropping frequency, and also the livestock density on agriculture areas plays a huge role on environmental impacts and also on the intensity of the land use. And we did a study where we wanted to look at the relationship between agricultural land changes, cropland area. We looked at cropland and looked at where did cropland decrease or where did cropland area increase. And we wanted to put that in connection with land use intensity changes, here also for cropland. But for quantifying intensity, you have to look at all the input factors, which is quite difficult. But land use intensification often is done to increase the output, to get more productivity of an agricultural land. So we looked at productivity changes and taking the crop yield as an indicator of productivity changes. And so when placing a country or a region on this axis of yield versus cropland area changes, we can, for example, be in a region where there's a yield increase occurred, but at the same time, cropland area has also expanded. And we would say that this is an indication of the rebound effect it could be a rebound effect of land use intensification of a certain crop type, which gives market initiatives to further expand agriculture production. And there's another concept which is on the other side, where there's yield increases happening, but at the same time, the agricultural land is saved and it even remains stable or it's been abandoned. And this we would give or classify as fitting into the concept of land sparing. It's often claimed that we need to have more sustainable intensification to spare the land so there's not so much cropland expansion happening into natural ecosystems. So we wanted to look a little bit of where do different countries across the world find themselves in this system here of yield versus cropland area changes, and do we find evidence or indications of such a land sparing or a rebound effect? And this plot shows all the countries of the world having also the same placement again with the area changes, cropland area changes on the x-axis and the yield changes on the y-axis. And the countries are color-coded by their income level. And what we find here is that high-income countries, which are the blue dots, are mostly located on the left side. So we see that high-income countries have intensified, the yields have increased, and at the same time they have reduced their cropland, which we have also seen with the cropland abandonment pattern in the map before. Whereas lower-income countries, the orange dots here, tend to be more on the right side here. So we see that there's maybe some less intensification, or the yields could not increase as much, but there's a more area expansion of cropland that has occurred. Again, we're looking at the 6 decades, so from the 60s to now. And what here is striking, that we have some countries, and they're mostly from these emerging markets, the middle-income countries of the tropical regions that have expanded very, very much, and also the yields have increased a lot. And here we can see a little bit this rebound effect. We have to further investigate that because we did also correlation analysis and looking more into the Granger causality between yield and area changes. But we can say that there's, for some crop types in tropical regions, and that's mostly soybean and palm oil, where there's the increase in efficiency and in productivity has further curbed the cropland expansion. And so this would be an indication of such a rebound effect of land use intensification. Coming to the drivers of land use change. Why does land change, and what are the driving factors? Can we quantify, can we identify those? And for this, we started with a study of collecting a lot of socio-economic, but also environmental indicators that are either indirect or direct drivers of land use change. And this is a long list. It's like around 40 indicators, but they can be grouped into the economic perspective, the demographic perspective, and also politics, and institutional effects. And this is the indirect side, and in the direct, production-related indicators, and we can also have some environmental effects, of course, like droughts, precipitation, temperature anomaly, and also some wildfires. So there were different indicators collected. Some of the indicators were only available at a country scale, and some were spatially explicit with very higher or lower resolution, but we could have a spatial connection to the land use and to the mostly environmental indicators. And we did this analysis only at the country level, so we aggregated the land use transition rate for some of these land use transitions, and we had time series of all these indicators over 60 years, annual time series, and we tried to connect the time series of the indicators with the land use transition rate for different land use transition types. And we used a causal network analysis to try to link those time series and see whether there's causal linkages between some of the indicators. And what comes out of it, this is already this showing only the most important, the most significant driver, and it's showing the category of the driver. So it's now split into this politics, economy, demography, production, and environment. And this is a partial correlation index that gives how strong this correlation would be. And we see that politics and economy are globally most important, although the correlation is not super high. And when looking at different regions of the world, this pattern changes a bit, but we also have to look more deeply into the individual drivers. There are large uncertainties because also there's interconnected indicators involved. And here, for example, we can also look at what are the individual driving factors, and we see that also in some regions there are subsidies closely connected to the land use transitions. And there's also some results we're not really sure if that's a spurious correlation or it's really a driving factor, so there's still some analysis to be done in this regard. I move on to the impacts of global land use change. Why do we even care? What do we know about the impacts, and what can we say now about impacts on the environment? Let's have a look at the global carbon cycle and only look at the proportion of the land use relevant. And we can see that the land use change component, which is this orange arrow, is a net emission component. So land use change is around 1/3 of the cumulative CO2 emissions since 1850. And this is showing the years from 1850 to like 2020. And if we zoom in to the more recent time span from 1960 onwards, we can see here only the land use contribution. And we also see that with these dotted lines that there's a huge uncertainty involved with estimating and quantifying the carbon impact of land use change. And this is not only due to different models and different model paradigms, but also because of the land use data that is used to measure this. Some important land use changes that are linked to if land use is either a source or a sink, is like forest area changes, but also forest management, forest degradation, and also agricultural land use change. As we were looking at it, like we see just classic conversions of like natural areas to cropland, but also forest regrowth after agricultural abandonment plays a role. And here with this tractor symbolized all the different management inputs we put into the system. When looking at the different world regions that have contributed to the CO2 emissions over time, we also see that, the global north, North America, Europe, Eastern Asia, has contributed more than the global south. And here again in orange, we see the part which is coming from the land use change, and the forestry sector. But we don't only have climate impacts, we have also biodiversity impacts, of course. And we're coming from a long history where natural ecosystems have more and more been transformed into anthropogenic ecosystems. Now we have large part of intensive agriculture, urban areas, but there's also some protected areas, protected lands. And from the IPBES, it is said that land use change is over 50% of the human impacts on terrestrial and freshwater ecosystems. So it's a huge component, and there's a lot of different effects that are caused by land use change, most importantly, habitat, fragmentation, and loss. Land use change, many studies have said or have found that there's a reduction in local species richness, but also a change in species composition and a decrease in species abundance. But this, of course, depends a lot on what species you look at and which regions. And there's also different effects of different land use transitions. So also here we have large uncertainties, but studies have shown that the terrestrial biodiversity has declined by more than 20%, the global biomass has halved, and wild animals have declined by more than 3/4 due to mostly land use change and other anthropogenic processes. But here we have also taxonomic bias, so where more data are collected, we know more, of course, and so there's still a lot which is not quantified and not well explored. When looking at the different components of land use that are affecting the biodiversity, here it's quantified with the number of species as an indicator, the number of species that are lost. We see that cattle and agriculture, especially cattle farming, have had the highest impact. But when we look at the changes, we see that especially oilseed production, so this is looking at the changes here, has increased its biodiversity a lot. We have a higher impact in southern regions, in the tropical regions, but this is also because there's more biodiversity in some of those regions. And also the area of land use change we have seen is more in the southern region, so these north-south differences are there, but there's often this linking role of international trade. So where the products of agriculture which are produced in the tropical regions, where do they go? This is mostly exported and imported again from the northern global north regions. And yeah, so there's a huge telecoupled effect by trade and globalization. So impacts, interactions, and feedback. So we have seen there's still large uncertainties in studying land use impacts. There's a lot of bias, scale dependencies, and also it depends on where data is available. And overall, it's complicated, like it always is. And coming back to the planetary boundaries, that there's this connection, of course, between the land system, between climate and fresh water and geochemical flows. And these interlinkages makes it even more complicated to disentangle and nail down different contributors. And we have crossed the boundary, but so what? How can we reduce this effect? How can we reduce this trend? And there's many different solutions discussed and applied at different regions, at different scales. Many people talk about nature-based solutions, about changing the way we produce food, trying carbon farming, integrating agriculture with nature-friendly practices, and also reducing the land use displacements. And here, of course, we need policy. We need to tackle not only the supply side from the agriculture production, but also the consumption and the demand side of things. And yeah, of course, there's this strong need to change the food system. And now I want to do a last step of moving from the past a little bit to the future. In our group, we do also a lot of land use modeling, and it's also to support, to find some of these solutions. So, of course, the land use modeling starts from a solid basis, so we need to have this understanding of the past and know where we are coming from. But it can support spatial planning and also find targeted climate and environmental policies. And we model the effect of land use change on the society, but as well as the environment. And we model the behavior and the processes that involve land use change. And in our group, we have developed an agent-based model called Crafty, and this is available at different scales. So here I show a Germany example. It's an agent-based model, so here, of course, in the center is the land use agent. And this is a farmer, it can be a farmer or a forester. People make decisions in the land system, and we try to model these decisions. And the land use agent here can compete for the use of land, and they can also collaborate with each other. So there's competition and there's collaboration. Those land use agents, they supply different goods and services to the society. And this is this loop here, the society also places demands. So society needs different things from the land system in different scenarios. And so a big part of this modeling is scenario development, of course. Which scenarios do we take? How is society evolving? But also how is climate and how is the biophysical properties of the land, how do they change the way we can produce the goods and services? So this is a bit the setup. And I just want to show you a little bit how different land use patterns can be for the future. This is a result for two different scenarios. You see on the left side a quite sustainable green growth scenario, and on the right side, scenario of fossil fueled development in Germany. And there are different land use types. They are shaded a little bit by their intensity. So the stronger the colors, the more intense the land use. And from the first glance, you already see Okay, very strikingly, you see that there's a huge urbanization in northwestern Germany in this here fossil-fueled scenario. And you can also see that there's the different shading. So in the green growth scenario, we have paler colors. So the land use is not intensifying, but there's a reduction of land use intensities. We have more organic farming, more sustainable practices included in agriculture, whereas here in the fossil fuel development, we want efficient land use, we want efficient production, and we have more intensification. So some of the effects and some of the land use processes in the SSP1 scenario, green growth, we have more protection, more nature protection, conservation areas. We increase peatlands in Germany. We have also an increase in forest area and a reduction in management intensity. And on the other hand, in the fossil fuel development, we have a strong urban expansion, also has to do with migration due to climate change in other regions. And we have increased management intensity both in agriculture and forestry. Also, the energy production, of course, is totally different in these scenarios, which also has to do a lot with the demands we have on the land. So here I put a butterfly as a symbol because, of course, these land use changes have different effects on the ecosystem. We have an increase in species in this scenario, and in this scenario we would have more economic benefit, but a more damaged ecosystem. And so, yeah, we are still playing around with these different scenarios and want to apply different policy measures and how they affect the land system in Germany here. So with this, I want to close the talk and just summing a little bit up what we have seen. We have, of course, we have extensive land use change. We have changes that are globally divergent. We have these differences between north and south, between different world regions. But we also have drivers that are very much interconnected, which are difficult to quantify, and where there's spatial and temporal connections between socio-economic and the environmental factors. There are still large uncertainties, especially in estimating the impacts on a global level, and the solutions are needed at different scales. Policy is important here. We have to look both on demand and the supply side when talking about agriculture. And when we want to look into the future and make plans and better inform policy, we also need to be aware of the context the context is important, and we have this high dependency on the scenario, on how land use is evolving and how also the options for political actions might change completely. And with this, I thank you a lot for the attention, and I'm happy to receive any questions.
Brilliant. Thank you very much, Karina. That was really great. I need to find the microphones.
Yep.
No, they're easy to find. Okay, so... Yeah, question here from Anna.
Thank you. Super nice talk. Very interesting. This wasn't clear to me because you reconstructed land use changes back to 1960s, and for that you relied on products that are already available, like the ESA land cover maps and Copernicus maps. But as far as I'm aware, they go back to early 90s, 80s maybe max. So how do you, go back like 20 years in time? Do you assume similar land cover and then you just rely on the FAO stats, or how did you go about it?
Yeah, thanks for the question. It's also one of the problems of doing such a reconstruction, because you're right. Most high-resolution land use or land cover products from Earth observation are only available to the 90s. There are some coarser resolutions. They are available in the 70s even. So I have data from 70s onwards. But the more you go back in time, the scarcer the data is. And of course, in the 60s, there's no observational data stream that gives us the land cover. But what here I had to take the trends from the 70s and kind of extrapolate the spatial trend into the past. And this is something which gives uncertainty and it's, of course, the uncertainty increases if you go back to the 60s. But yeah, this is one drawback of this. And of course, there's then more reliance on this FAO statistics because the spatial patterns could have changed but are only extrapolated from the trends we have seen in the years after it.
Can I come to you in a second, Mario? Because I've got a question kind of related to Anna's question. So is it that the spatial and temporal resolution and how far back it goes differs in different parts of the world? And is this why you've got more evidence of this dynamic change of gains and losses in places in the global north like Europe compared with the global south where you've got less fine resolution and less length of data, so it just looks like a change in one direction? But actually, no, it might be more dynamic in Europe and more recent.
In fact, I think it's a mixture because I think it's playing a role that, of course, in Europe, I used also not only global data sets, but also regional data sets like Korean land cover being available for Europe. So I think there is an effect of data availability, but also in Europe we have more smaller scale land use types closely together. So I think it's still somehow both effects are included. So there's something that is a real effect, but of course we have a bias on data availability like all the global studies have, I think. Yeah.
Hi. Thank you for the presentation, it was amazing. I have a question about, it's really related with this question, it's about what happened with the HILDA 1, with the project. It was from Europe since 1900 till the present, and I never saw more of this, and then you present the HILDA Plus, it's our award. So I don't know what happened with this project.
Yeah, I didn't mention it, but it like HILDA Plus, that was my PhD project, and it started from the HILDA project. Okay. Richard Fuchs, the HILDA guy, he was my supervisor in the PhD, and he had this idea of doing the same data set, but on a global level, and he kind of advertised his PhD position, and I came and did it. So he did no longer focus on a European data set, so I think it's not even there anymore. I'm not sure, but it's the same like logic of how to harmonize data, but now expanded on a global scale. And yeah, we're working both together on this global scale HILDA Plus now. Yeah.
And are you validating this data set with, for example, deforestation with insect decline or something with this? Mm-hmm. I don't know.
Yeah, so we had some ideas of doing like also more regional validation, but so far we didn't do it yet. So but I think it's still an open thing we want to look into to make, to look at specific regions and see how well it can cover those changes that are, of course, much finer than what we even do at this 1 kilometer scale.
Well, for example, in Spain, we have a aerial image since 1915s. So it would be useful.
Oh, yeah. Super good, yeah. Yeah, maybe it would be a good option to start where we have the data and
I suppose that our country has like an old picture, but it's difficult to find it.
Yeah.
Okay, thank you.
Hi, so super nice talk, as already people said. I have a question, because I think you can have the data, but you present shift in land use, just in the absolute, so it shift from that to that. But have you in mind to look at time in shifting? I mean, is it quicker to go from, I don't know, forest to agriculture or agriculture to urban? Because I know that in France, we look at that and we see that since you have agriculture, you easily shift to urban, whereas from forest to agriculture, for example, it could take more time and stuff like this. And I hope it will be super spatially different in terms of area.
Yeah, it's a very good point. So what we did when we do this kind of temporal dynamics for different world regions is also look, some of the transitions are a single event transition. So you have 1 year where the forest is gone and there's just agriculture on it. And some, like forest regrowth, it's more there's multiple change events in our data set that are involved. So we have then maybe the agriculture is abandoned and it's first like from a cropland going to an unmanaged grassy shrubland environment. And then it's taking years until there's a real forest there. And I think it could be interesting to look more into these, like the transition time, not only, okay, when did the change occur and how do they shift, but also more, okay, slower and faster transitions. But it's a bit difficult with these discrete classes we have, because I think we need more finer land use types, because of course we only show the dominant land use in a 1 kilometer pixel. Reality is more complex and we have this gradual changes, and I think that's a bit the challenge we have to do here.
Yeah, because I think as ecologists is one of the big questions like, in terms of lag effect. I mean, like I think many of people are interested to say like if we are changing from a forest to a grassland, then to urban or forest to urban directly. What are the effects of the community? Because you can see different communities which are not based on the land use, but more about what was in the past, and because species still there because there were grassland species and stuff like this. So I think it will be amazing that one time we will have this data available.
Yeah, I take this as an idea also to shape future projects, because I think this is something we can still integrate in some analysis. Yeah.
Thanks a lot.
Hi again. So I was wondering, probably you're aware of the height data set, which looks like to land cover like really back in the past. I wanted to know your thoughts about this data set, like, because I mean it's already hard to go back to the 1960s, especially looking at land use transitions you did, but going back to thousands of years ago. What do you think about it? It's a bit of a wild guess. Can we rely on that? Can we do better? And in relation with this, what are your thoughts about future land cover maps that are also available in different papers? Yeah,
so regarding the height data set, I think it's the basis of all the, also the land use input for climate models at the moment, because height data set it's basically a model that relies on population estimates. So basically population is driving it all. There's remote sensing-based data included, but only, of course, only at the recent period. And I'm currently working together with the people from HEID database in a project. It's a European project where we try to combine the approaches and match HEID with HILDA Plus. So this is one idea. I think so what I think of HEID is that of course you have these uncertainties. You cannot claim that height has to do with observational data, because you rely on the assumptions you make that the population development was like that in the past, and so are the linkages the same we have known in the recent past are the same in the more historic past. But I think it's the best we had so far for doing modeling, and so there's ways to improve, and I think these steps are taken or at least started. And so about future land cover data sets, so I think there's so much out there which now we have on tracking and observing what happens now in real time, and I don't know, not even yearly, but more like even weekly data sets. And I think it transforms of what we know about now, but it doesn't bring us so much closer to that what happened in the past. But I think maybe it's not so important for future modeling to know exactly what happened 1,000 years ago. But I think it's a good step to have this better distribution or this better representation of land cover now, and that this is flown into the modeling community as well. One major problem and obstacle I see is that land cover doesn't show land use, and that's, yeah, and so you see, of course, what's there on the land surface, but you cannot see for what it is produced, where does it go, what's the purpose, and what is the inputs. And I think there we need to do the link.
So you wouldn't dare to take the step of trying to model future land use just yet. Let's put it like that. Because I think like projecting land cover into the future is already quite hard. I mean, of course, there's a lot of uncertainty, but then adding land use on top of it, do you think anybody's crazy enough to attempt this, or?
Yeah, I think so. I think it could be done. It's showing like, okay, if we just extrapolate recent trends, what would happen? But we are a bit blind in this land use. Even if we think of land use now, there's a lot of data which is not spatially explicit, which we have to still link to the land cover. And I think this is something we need to establish, and then we are better informed. Yeah.
Okay, thank you for a great set of questions. Thank you for a great set of answers and a brilliant seminar. So thank you very much, Karina. I guess we'll probably go down and have a drink at the kiosco now, but you're around until tomorrow, yeah? So if you want to have a chat over the next 24 hours, then I'm sure Karina will be very happy to speak to you. Okay, thank you.